All right, hello everyone. So we're going to be going over question 3, sorting design decisions. But before we get into it, I just want to look over our sorting cheat sheet and remind ourselves of the runtimes and some aspects of the algorithms that we'll be working with in this question. So the algorithms that will be able to choose from for question 3 include insertion, selection, merge, quick, and heap sorts. So the worst case runtimes for all of the algorithms except merge and heap sort are going to be n squared, where n merge and heap sort are going to have n log n runtimes in the worst case. In the in practice or the average case, insertion and selection sort have n squared runtime, but merge sort, quick sort, and heap sort have n log n runtimes, which is basically the best we can do. And then the best case scenario, insertion sort and heap sort are going to have linear runtime. Selection sort is going to have n squared runtime, and merge and quick sort are going to have n log n runtimes. In terms of space complexity, or whether or not they are in place sorts, every sort is going to be in place except merge sort, meaning that merge sort will use extra data structures or extra memory to run the sort. And in terms of stability, every sort is going to not be stable except insertion sort and merge sort, meaning selection sort, quick sort, and heap sort are not stable. So hopefully this was a good refresher, and I really recommend that you keep the sorting cheat sheet next to you as you work through any sorting problems ever. Yeah, so now we can go ahead and get into our sorting design decisions. So part A asks us, suppose we want to sort an array that contains 50 strings. So which of the following 5 algorithms is the best choice? And the 5 algorithms are also the ones we just reviewed, which is good. But yeah, so some main ideas for this question we want to think about is the fact that we're only dealing with 50 strings. And also, when it comes to computer programs, this is not a very large input size. So we could choose from a lot of the options we have here and be completely right. But in our case, we're going to go with insertion sort. So the reason for that is because it's fast on smaller inputs, and even though its worst case runtime is O of n squared, it has a low constant factor. So we would be okay if we used insertion sort in this case. But also, we could have used merge sort, quick sort, and heap sort. They would have been completely reasonable choices for this question. Right, moving right along to B. B says, suppose we have an array that contains a few hundred elements that is almost entirely sorted, apart from 1 or 2 elements that were swapped with the previous item in the list. So which of the following algorithms is the best way of sorting this data? So we're dealing with the same algorithms we did last time. So the main idea for this question, the thing that should jump out to us initially, is that the array is already almost entirely sorted. So we already want to start thinking about the cases for our different algorithms and which algorithms would run well with almost already sorted data. And also that we'll only have to move a few elements and swap them with their neighbors to get our sorting correct. So we want to look at our list of elements and think, okay, so I have which sorting algorithm is going to work best with an already almost sorted array, and then which is going to do the least amount of work when it just comes to swapping and moving some elements around. And hopefully the first thing that jumped into your mind was insertion sort, which is going to be the correct answer here. So the reasoning for this is that it's going to run in linear time for inputs that are already or close to completely sorted. And yeah, so this is the best runtime that we can get, and insertion sort would be the right answer for this question. Right, moving to C. C asks us, suppose we want to sort an array of ints, but also want to minimize the amount of extra memory we want to use as much as possible. So we're going to deal with the same algorithms we have been. But the main idea here that we should be thinking about is the fact that we don't know anything about the input. All we know is that it is an array of ints, but we don't know about the state of the input like we have for the last times, like, oh, it's got only 50 strings in it, or oh, it's almost completely sorted. All we know is that we're dealing with an array of ints, some array of ints. So, and then the second thing that maybe jumped out to you before even the state of the input is the fact that we want to minimize memory. So already those words should ring alarm bells in your head and should remind you that you want to select an algorithm that is going to be in place or have constant time complexity. So judging from the algorithms we have on our list here, we would go with quicksort. So quicksort is again in place, so it would use no extra memory, and we also don't know anything about our input. But in the average case, quicksort runs pretty efficiently with n log n runtime. But we also could have used in place sort heap sort here for the same reason. So it would be a in place sort, so it would use no extra memory, and also it would be an efficient sort like we want. All right, moving along to D. So now we're going to leave behind our algorithms a little bit, and instead of picking algorithms, we're actually going to pick inputs for certain cases. So suppose we have a version of quicksort which selects pivots randomly to create partitions. Explain how you would build an input array that would cause this version of quicksort to always run in O of n squared time. So just to remind you, O of n squared is the worst case possible runtime we have for quicksort, and we already know how we select our pivots. So we select them randomly just from whatever we have available in our input array. So now we're going to have to think about the state of our array. So what would the array look like, and what would happen when we tried to run quicksort on it? So the main idea here is that to get good performance time from quicksort, usually we'll just partition the input array into roughly halves, right? But for bad performance from quicksort, aka O of n squared runtime, we need to be able to do the opposite, meaning we don't want to have it so that our array gets partitioned in half each time. And the way to do this would be to have an array with all duplicate elements. So the reasoning for this is that each time you partition, all elements will fall onto the left side of the partition, so since they will be less than or equal to the pivot, and that means that we'll always go with O of n squared runtime to actually sort this array of duplicates. So moving on from D to the final part, E, we're actually going to take this worst case that we have and try to optimize it. So how could you modify both versions from quicksort, the in place, not in place implementations, so that they no longer display O of n squared behavior when they're given the same inputs? So the input is going to be an array of all duplicate elements. And we want to be able to make it so that we don't end up, when we use our pivot, we don't end up with all of our values on one side of our pivot. So the main idea here is an array with all duplicate elements will again always be sorted in O of n squared time because all the elements will fall on the same side. But we want to optimize for this. And one way, there's plenty of ways we could do this. But one way we could go about this would be to partition the array into 3 groups instead of 2. So here's how we would do this. We would have the left group contain all of the elements that are less than or equal to the pivot, but then we would have the middle group, the left group would contain all the elements that are less than the pivot. The middle group would represent duplicates or elements that are equal to the pivot, and the right group would represent elements that are greater than the pivot. And we would just not do any more sorting on our middle group. We would just say, okay, like these are already sorted since they're all the same element. We don't have to worry about it anymore. Let's just concentrate on our left and right groups. And for that reason, there would be no more work left to do for the duplicate group. And this would lead to a modified algorithm, or our modified algorithm on a duplicate array would sort in O of n time rather than O of n squared. And the reason for that is once we choose a pivot and partition into our left, middle, and right groups, everything in our array would end up in our middle group. So we would be done sorting. And yeah, that is it for question 3.